All right, so now we're going to look at Mergesort, another sorting technique. And in lecture 6, we're going to look at yet another sorting technique called quicksort. But you may be getting tired of sorting techniques, but it really is important to realize that Mergesort and quicksort are profoundly different in their approach to sorting than the three basic approaches that we've looked at so far. Recursion is going to play a big role in our approach to Mergesort and later on quicksort. The strategies involved in both of these algorithms are often said to be divide and conquer strategies. It essentially means that in trying to do the original problem, you chop it up into sub-problems and you attack the sub-problems in the same manner as the original problem, and then somehow you put it all together. You'll see how this works for both Mergesort and quicksort. They are quite different, but they both rely on this divide and conquer strategy. Okay? Eventually, I'm going to have you run the sorting program, and it's my intention that when you do that, you'll get a profound sense of how much faster Mergesort and quicksort are in contrast to bubble sort, selection sort, and insertion sort. And I'm talking about not when you have a small list, but when you have a substantial, a pretty big array of numbers, like say 10,000 numbers. Okay? The evidence will make it very clear that Mergesort and quicksort are a lot faster. Later on, we're going to discuss something called heaps, and we'll have brief contact with yet another sorting algorithm. I realize that you would probably be tired of sorting algorithms at that point. Anyway, the remaining sorting algorithm that we're going to look at later on is called heap sort, and we'll not be spending very much time on it. Mergesort requires the use of a second array, another array that's as large as the original array that you want to sort. And this auxiliary array is used as a kind of a scratch pad, as you'll see. Therefore, it's often said that Mergesort does not sort in place, meaning that it requires extra memory, substantial extra memory to sort. Okay, so I said that the strategy is more sophisticated. It's recursive, divide and conquer, and so on and so forth. But really, it actually is pretty simple thinking. And the essence of the strategy is pretty straightforward. Basically, it comes down to this idea. You want to sort an array. So what you do is you at least conceptually chop the array into two halves, the first half and the second half. Okay? Now, suppose you can sort each of the halves. You will wind up doing that recursively. So we'll recursively sort the first half and recursively sort the second half. Well, how does that benefit us in terms of getting closer to sorting the whole array? And the fact is, it actually is a really big benefit. If you can sort each half, then it becomes possible to so-called merge them together into a sorted array, and to do that quickly. I want to show you a figure intended to convey a sense of this recursive so-called divide and conquer strategy that underpins Mergesort. Let's keep it simple. Let's say we're trying to sort an array of size 8. So my example here, I'm imagining that the array has a power of 2 numbers in it, but Later on, we'll dispense with that simplifying assumption. Okay? But for right now, let's assume specifically we want to sort an array of size 8. Okay, so we can divide that array into two halves. The first half is a subarray consisting of 4 numbers. The second half is a subarray consisting of 4 numbers. Okay, we would like to sort each of those subarrays. How do we do it? Well, I hope you guessed that we again use recursion. So let's say to sort the left subarray, we will chop that into 2 subarrays, each consisting of only 2 elements. Okay? So here is the figure that I have in mind. This cloud at the top at level 0 represents the original problem, our ultimate goal, to sort an array of size 8. Okay? We have divided that into 2 subproblems, each of which is a problem of sorting a subarray of size 4. Okay? The cloud off on the at level 1 on the left represents sorting the first half of our array, and the cloud on the right at level 1 represents sorting the second half. Each of those problems, as I said, in turn gets divided into 2 subproblems. And each of those subproblems is really just a question of sorting subarrays consisting of only 2 numbers. Okay, so that's level 2. At level 2, there are 1, 2, 3, 4 clouds. Each of those clouds represents a problem of sorting an array of size 2, or subarray of size 2, just 2 elements. Okay? Again, those are attacked using the same merge sort recursive thinking. You take the subarrays of size 2 and you divide it into 2 subarrays, each of size 1. Okay, now that takes you down to level 3. Level 3 consists of 8 trivial subproblems. Okay? And I think you know why I'm saying they're trivial. Each of those subproblems is the problem of sorting an array of size 1. Well, if you have an array of size 1, or subarray of size 1, there's only one number. It's already sorted, so it's trivial. Okay, so there's really no work to be done at level 3. The problem is solved as soon as it's stated, I guess. Okay. There's obviously a missing ingredient here. We haven't yet talked about the merging. How do you take the solutions and merge and so forth? We're going to get to that. But the idea, so that you get it, is you've solved the problems down at level 3, and then you go back to level 2. Merging takes place at level 2. You wind up solving the level 2 problems, and then you go back up to level 1. Merging then solves the level 1 problems. As soon as you've solved the level 1 problems, you've sorted the first half of the array consisting of 4 numbers, and you've sorted the second half of the array consisting of 4 numbers. So you go back up to level 0, where you finish off by merging those 2 solutions to obtain a solution to the original problem, an array of 8 numbers in order, okay, sorted. Let's run through an example, and here I'm going to not assume that the array size is a power of 2. Let's take array of size 6, okay, and see how merge sort plays out, at least in part. Well, I guess the point here being that our focus will really be on the merging here, okay? All right, so in the beginning, we have an array of 6 numbers, C3, 17, 92, 5, 72, 21. We conceptually split that into 2 subarrays, the initial 3 and the final 3 numbers. So it's nice visually to separate them like this, but it's also important to realize that we're not really doing anything in terms of moving data around yet in memory. This is just a conceptualization of things. Okay, now we use recursion, and here I want you to trust. It's a funny thing about recursion. We basically talk about trusting that the recursive calls work. And honestly, as you go forward and try to program recursively, it actually is beneficial psychologically and so forth to trust that recursion works. Okay, so if we could recursively sort each half, then we would end up in this situation. The left half becomes sorted and the right half becomes sorted. Okay? The entire array is not yet sorted, but as I said, it's helpful that the left half is sorted and the right half is sorted, because now it gives you the opportunity to merge them together. This is going to require the auxiliary array. So here we are. This is how the merging goes. The top the top part of this is obviously the original array, and the bottom part of this is the auxiliary array. I have arrows, 3 of them. Okay, I've got an arrow, basically help me keep my place. Later on in actual code, these will correspond to indexes, variables, indexes used to index into the arrays. So anyway, there's an arrow pointing to the first entry in the first half of the original array. There's an arrow pointing at the beginning of the second half of the original array. And there's also an arrow pointing to the beginning of the auxiliary array. Then we start off by taking the 2 entries that are being pointed to in the original array's halves. Okay? Let's refer to these numbers as the entries being considered. Okay, so in the left half, we're currently considering the number 17. In the right half, we're currently considering the number 5. Okay, what we have to do to get this merging business started is we have to compare those 2 numbers, and whichever one of them is smaller, that number has to get copied into the auxiliary array at the position being pointed to there. All right, well, in comparing 17 and 5, it's discovered that 5 is the smaller of the 2 numbers, so 5 gets copied into the first position in the auxiliary array. After that, we advance the arrow in the auxiliary array, and we also advance the arrow in the subarray from the original array that we copied from. Okay, we copied from the second half of the original array, so we advance the arrow in the second half of the original array. And then we repeat. Okay, so now we're considering 17 from the first half, and we're considering 21 from the second half. We compare those 2 numbers, discover that 17 is the smaller of the 2, and therefore we copy 17 into the auxiliary array. Again, after copying 17 into the auxiliary array, we advance the arrow in the auxiliary array, and we also advance the arrow in the first half of the original array because we just copied from the first half. Okay? We continue. We're going to compare 63 with 21. 21 is the smaller, so we copy 21 into the auxiliary array. This continues until we run out of numbers to look at in one of the 2 subarrays. Okay? Eventually it's going to happen that we run out of numbers in one of the two subarrays. In this example, that isn't going to happen until very close to the end. If you step through it, and I definitely encourage you to fill in the missing steps here, we will have copied 5, 17, 21, 63, and 72 into the auxiliary array, and at that point there's nothing left to look at. We've used up all the numbers in the second half of the original array. Okay? But there still is a number in the first half that we haven't copied yet, namely 92. Okay, so when we get to this point, it's simple. We do what you probably would expect. We just copy the remaining numbers from the subarray that hasn't been used up yet. And so in this case, we just copy 92 from the first half. And voila, we now have a sorted array. The 6 numbers have been sorted. Okay. The sorted array, though, is the auxiliary array. Okay. The original array is 17, 63, 92, 5, 21, 72. That's the condition of the original array. But the auxiliary array is sorted 5, 17, 21, 63, 72, 92. Well, of course, we want the original array to be sorted. Okay? But that's very simple. All we have to do is copy back the auxiliary array into the original array. Okay? So we take a pass through the auxiliary array. After we've copied the auxiliary array back into the original array, we're done. Okay? The original array is now sorted. But let's see, a couple slides back, what did I do? I sort of snapped my fingers and magically sorted each of the 2 halves of the original array. Okay, I sorted the first half and the second half, and you let me get away with that. So, well, the question is, how do those 2 halves get sorted? Okay, how does that really happen? How can we actually make the program sort each half? And I hope you know the answer. The answer is we attack those problems recursively. Okay? The way we get the first half sorted is exactly the same way as we've just discussed getting the entire array sorted. We take the first half, we chop it into 2 parts, sort each part, and then merge them together. Well, you may be a little squeamish about that because why? The first subarray consists of 3 entries. So how are you going to cut that into half? Well, you can't exactly cut it into half. So you settle for chopping it into 2 subarrays, one consisting of 2 elements and the other consisting of just 1 element, and it doesn't matter which is which. So the first half might consist of 2 halves, the second half might consist of only 1, or vice versa. But anyway, you recursively attack the problem, you sort each half, and then merge together. Just to reiterate something, the so-called base case of this recursion is when you get down to an array of size 1, and when that happens, you don't have to worry about it. Sorting a subarray of size 1 is a no-brainer. There's nothing to do. Okay? In every other case, if there's more than 1 element in the subarray, then you have to split the subarray into 2 halves, and you want to do that so that the 2 subarrays have the same size or as close as possible to having the same size. So just some minor points here. The subproblems involve sorting subarrays of the original array. So if you're sorting a certain subarray of the original array, then it requires using corresponding subarray in the auxiliary array. I've made this point already, but let me make it again. I don't want you to be confused by the diagrams. To dramatize things, I visually separated the two halves of the original array, but that's only a conceptual aid. In reality, we're not moving anything. So, as we did with the other three sorting algorithms that we've looked at so far, the time has come to take a look at the code for merge sort. And as before, this code is used in both the Java and the C++ sorting code that's provided at the course site. Here's the code that I use in the sorting program that implements merge sort. Okay, so the function merge sort here has 4 parameters, A1, A2, left, and right. The first 2 parameters are arrays of numbers. They happen to be double precision floating point numbers, but really they could be anything. I could have arrays of ints here if we want. So A1 is the array that we actually want to sort. And array 2 is simply the auxiliary array that we're going to use as a scratch pad. Okay, the third and fourth parameters, left and right, specify the beginning and end of a portion of the array that we currently want to sort. Okay, so of course we want to sort the entire array in the beginning. The first call to merge sort will presumably be made to sort the entire array. But since we're going to use this function recursively, we need to design it so that it's capable of sorting just a subarray. Okay? A subarray that begins at position left and ends at position right. There are 4 local variables, I, j, k, and middle here, and we'll get to them in a second. Okay, the statement if left is less than right, followed by curly brackets, and you'll see the matching curly bracket on the next slide. But anyway, there's a whole lot of code in between those 2 curly brackets, and that code is only going to be executed if the left index is less than the right index. So if we have left equal to right, well, that would mean we're trying to sort an array of size 1. And as I said, if we're trying to sort a subarray of size 1, then there's really nothing to do. Okay, and we'll see that this program is going to basically do nothing at all in the case if left is greater than or equal to right. But assuming that left is less than right, we proceed as follows. We compute middle to be the average of left and right. Okay? It's going to effectively chop our subarray into 2 halves. Okay? The first half consists of everything from position left to position middle. And we call merge sort in order to recursively sort everything from position left to middle. Okay? Then the second half is everything from position middle plus 1 to position right. And we now make a second recursive call to sort everything from position middle plus 1 to position right. Now, once we've sorted each half of the subarray that we're trying to sort as a whole here, then of course it's time to merge the two halves together, just like we did earlier in the example with the figures. So here's how we're going to do that in actual code. We're going to use 3 variables to serve as indexes into the arrays. These indexes are I, J, and K, and they're very easy to understand. I, J, and K correspond to the arrows that we use in the figures. Okay? So I is going to be used for the arrow that we used in the first half of the subarray. J is going to correspond to the arrow for the second half of the subarray. And K is going to correspond to the arrow that we used in the auxiliary array. All right, so here again, let me remind you of the strategy that we have to follow. What is the algorithm that we need to follow to merge things together like we did before? Well, we have to compare what's in position I of the original array with what's in position J of the original array. And then whichever of those two numbers is smaller, that has to get copied into the auxiliary array at position K. And after copying into the auxiliary array, 2 indexes have to be incremented. K always has to be incremented. Okay, we copied something into position K of the auxiliary array, after which we have to increment K. All right? And we also have to increment either I or J, depending on where we copied from. All right? So here's how this is accomplished in code. We have a while loop here so that we can play this game repeatedly. And the while loop continues as long as I stays less than or equal to middle and J stays less than or equal to right. Well, what this is effectively saying is as long as I continues to index into the first half of the subarray and J continues to index into the second half of the subarray, we want to continue playing this copying game. Okay? As soon as I becomes bigger than middle, well, then it will have wandered outside the first half and into the second half. And if J becomes bigger than right, it will have wandered beyond the right half. Okay, so I think you get that. It's time to quit this loop when either of those things happen. All right, the next statement, the statement inside the while loop here, is very likely to catch your eye and very likely to bewilder you. The truth is it involves what's called the question mark operator, and it's very possible that you were not introduced to this operator in your introductory Java or C++ course. So I'll tell you what, I don't want to go too fast here. I'm going to defer discussion of this until later. So what I want you to do right now is trust me that this one statement here, A2 bracket K++ bracket equals parentheses, all this gobbledygook, that one statement is responsible for all that I just said. It compares what's in position I and what's in position J of the original array, and based on that it copies one of the two numbers into the auxiliary array and also increments the appropriate indexes. We'll talk about it in detail later. Okay, after that loop finishes, one of those two indexes will have wandered beyond the portion that it's intended to index into. But there remains the job of copying the remainder of the other portion into the auxiliary array, as we discussed previously. Okay. Well, the two while loops set up here are responsible for doing that job. Okay. The first one says that while I is less than or equal to middle, copy what's in position I into position of copy what's in position I of the original array into position K of the auxiliary array, and increment both index I and also index K. All right? So it's basically saying if we're not done, if we haven't yet copied stuff from the first half into the auxiliary array, we'll take care of that now. This while loop will guarantee that anything not yet copied from the first half will now be copied from the first half into the auxiliary array. Okay? The next while loop does the same kind of thing, but for the right half instead of the left half. So if there's anything left to copy from the right half, copy it now into the auxiliary array. Copy from position J into position K, and then increment J and increment K. Okay, so you should be able to understand that. Hopefully you've used increment operators in this kind of way in the past, where they're used as part of larger statements. And because the plus plus comes after the variable, the incrementing takes place after the whole statement. Okay, you should have done this kind of thing before, but let's be really careful about this. Saying A2 bracket K plus plus equals A1 bracket J plus plus means A2 bracket K equals A1 bracket J. In other words, copy what's in A1 bracket J into A2 bracket K. And then, after that's done, increment J and also increment K. All right? There's one final loop, and that's the copy back loop. When we arrive at this for loop, the auxiliary array, the portion, the subarray of the auxiliary array that we're trying to will be sorted. Okay? And all we have to do now is copy that back into the corresponding subarray in the original array, and that subarray of the original array will now be sorted, which is our goal, of course. So look at the code very carefully and work it out. Make sure that it makes sense to you. You can download the code and experiment with it if you like. Put in diagnostic messages, things like that. We discussed A1 and A2. We've discussed left and right, the fact that we're going to use merge sort in a recursive manner. When we call merge sort the first time, if we want to sort the entire array, we'll call it with left set to 0 and right will be set to 1 less than the size of the array, since that's the last position. We pretty much talked out all these things, but except that we need to take a careful look at this code right here. Okay, this is the one thing that I glossed over, and it's a very slick piece of traditional C programming. And I think it's very useful for you to get your head around it. Okay? As I said, the job of this code is to compare the entry at position I and the entry at position J in the original array, find out which of those is smaller, and then copy that into the auxiliary array, and then increment the appropriate indexes. Okay? So what does this question mark operator do? The actual construction is blah, 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 question mark, blah, 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 colon, blah, blah, blah. Okay? And it's very possible and understandable if this is entirely new to you. It's often ignored in an introductory course in Java and likewise C++. Okay, but it's pretty easy to understand. What comes before the question mark is evaluated. So in this case, it's a Boolean expression, and it's either true or false. In this case, it's the Boolean condition that A1 bracket I is less than or equal to A1 bracket J. Okay? If that condition happens to be true, then whatever comes after the question mark will be selected. Okay? But if the condition is false, then what comes after the colon will be selected. Okay? So in this overall statement up here, we're either going to be copying A1 bracket I++ into A2 bracket K++, or else copying A1 bracket J++ into A2 bracket K++. If we're copying A1 bracket I++ into A2 bracket K++, I say again, what that really means is we're copying A1 bracket I into A2 bracket K, after which I and K both get incremented. All right? Well, that makes sense. If what's in position I of the original array is less than or equal to what's in position J of the array, then we want to copy what's in position I into the auxiliary array at position K, and afterwards increment both I and K. But if that condition is false, then we want to copy what's in position J of the original array into the auxiliary array at position K, and after which increment both J and K. Okay? So think about that good and hard. If you understood what we were doing conceptually with the figures and the arrows earlier, then you only need to see how this code is exactly the right thing to make that work. We discussed the remaining while loops, so I won't dwell on it here. Once again, the code for sorting that's available in C++ form and Java form at the website includes this Mergesort code. Okay? You want to run it now. In a little while, we're going to talk about how to analyze the amount of time that it takes for these various sorting algorithms to execute. And at that point, I'm going to really want you to download the code, the program, and run the sorting program and really see the difference between these things. Okay, so hopefully you got a sense of how Mergesorts works. You might want to go back over the slides and take another look-see and make sure you understand all the details. No doubt the hardest part of this is coming to terms with the code. So once again, I implore you to really study the code. Take it seriously. If you want to be a programmer, you have to be able to read code. Okay? You have to really sweat the details on things like this. So please do that. And when you're ready, take the self-quiz on Mergesort.